Welcome. In this final video of 4.1 in week 5, we'll be looking at real zeros of a polynomial function. And we're going to review some of the properties of a polynomial function that we discussed earlier. We're going to start with this function that's not completely defined, but it has a lead term of negative 3x to the 7th. So when we look at the function, we should be able to answer a lot of the questions about these things, about the function depending on this lead term. So especially like the degree. So the degree is 7. It has a domain. Since this is negative 3x to the 7th, it's going to look like a odd power that's decreasing. So it's going to have some kind of graph where it has something happening in the middle, but it's going to keep going down as we go from left to right. We don't know what happens in the middle, but it's going to decrease because it's negative 7, continue for most of the area. So its domain is going to be from negative infinity to positive infinity. We don't have any restrictions on the domain. Number of intercepts, we can't tell exactly how many they have, but at most 7 because of the power of being 7 there. Number of turning points, we have at most 6. And we can also state, since the powers here are 7, 5, and 1, we can also say this is an odd function. And it has origin symmetry. Because of the odd powers here, 7, 5, and 1. So we could also state that fact as well. Now the end behavior based on this graph, as we go to negative infinity, that means we're traveling left on the graph. We're going to go up. So f of x goes to positive infinity. And as we travel to the right, we're going to go to negative infinity. We're going to go down. So that's our end behavior of this graph. So that's a little review. Even though you don't have all of the terms, we can still look at the powers. We can still look at the lead term. It's going to tell us a bunch of stuff. We're going to be able to say at most how many intercepts and how many turning points is, and we can describe the end behavior by the lead term. All right, so let's look at some of these, and hopefully we can do this. This is one of your worksheets in the documents folder. So if you want to look at this worksheet first, look through the worksheet and then come back to this. So this is on the matching one. So we're going to look through the graphs and try to match them up with their functions. So looking at the first example here, we have negative 2x plus 3. That's linear. So we're going to look through all of these. So that one's going to be a giveaway to being a linear function. So it looks like I have a stray mark right here. So if we look through these problems, only one of the graphs look linear, and that happens to be f. So f happens to be linear, so this would be f here. All right. Now the second one is a quadratic. It looks like a second power, so it's going to have one U-shaped curve, and it is positive, so that means it's going to be going up. So here's a possibility, but that one goes down, so that's not going to be it. And our other possibility is h. Okay, we don't have any waves in it because it's not a higher power than 2. So h is going to be our second term just based upon that. It's also going to have intercepts at 0 here. If we put 0 in there, we'll get 0 out. So that point does go through there. Okay, so we have that other choice there. All right, so here's our other one that's got a square in it. So it's a U-shaped curve, but it goes down. So that's going to be C, because that's my other choice there. So we've eliminated these parabolas and a straight line from this. Now we're going to get into higher powers now, so we're going to have to look at what the graphs might look like, how many turning points they have, and then so on and so forth. So on number 4 here, we have a cubed, and it's increasing, and it's odd, odd, even. So it doesn't have any symmetry. Odd, odd, even. There's no symmetry, but it's increasing, so it could be A, it can't be B, it could be or it could be B, it's increasing. It can't be D because D decreases. So it's A, B, and that's our choices. The other ones are, these are even because they go down going down, and this one goes up. So it's either A or B. So if we look at this though, we can only have 2 turning points at most. So this one has 1, 2, 3, 4 turning points. This only has 2, so it's going to be A because of the number of turning points. It has to be this one. This one has 1, 2, 3, 4 turning points, so that means it has to be at least an x to the 5th. And if I look through all of these, the only x to the 5th I have is number 8. So B has to be number 8 because of the turning points. Earning points to give it away. So that gives this function away because of the turning points. Has 1, 2, 3, 4 turning points. That means it has to have at least a power of 5. So it has to be at least x to the 5th. And the only x to the 5th I have is this one. So that's B. This one has 2 turning points. It's an x to the 3rd. It's decreasing. So x to the 3rd decreasing, that would be this one, negative. So D happens to be 6. And this is even, has symmetry. That means all the powers have to be even in it because it has y-axis symmetry. So we only have 2 choices here. We have 7, which has a power of 4 and a power of 3, and this one has a power of 4 and it has a power of 2. So this one's an even one, so this is going to be E because it has symmetry. And then the other, plus it goes down. It's negative. This one's positive, so it has to go up. And this one's the positive one, so this right here is G. G is a positive here. This is G. So we can use some of the facts to help us graph or identify graphs of the functions by looking at all of these properties of the polynomial function. The degree, the domain, the x-intercepts, the turning points, the end behavior. All of that will help us match graphs or look at a graph and take a look at what its properties are. All right, now we're going to do some examples of real zeros. So a zero of a function is when we have f of x equals 0. So we have 0 equals x squared minus 3x minus 18. And we're going to solve that. Well, this one factors into x minus 6 and x plus 3. So we have 2 zeros of this function, x minus 6 equals 0 or x plus 3 equals 0. So our 2 zeros are 6 or x equals negative 3. So that tells us in this function 6, 0 is a point on the function and negative 3, 0 is a point on the function. This is a graph of the function. Now let's take a look at the second example. So we have x to the 3rd here. So in this example we're still going to set it equal to 0. Right? We're still going to set it equal to 0. And we're going to factor this one as well. So this one also factors. We can take out an x because there's an x in each of these. We have x plus 7x, or x squared plus 7x plus 12. This factors again. X plus 3, x plus 4 to add up to 7. That means we have 3 zeros. 3 zeros are x equals 0 or x equals negative 3 because that makes that part 0, or x equals negative 4 for this part makes it 0. So we have 3 points that this graph goes through: 0, 0, negative 3, 0, and negative 4, 0 are all the zeros of that function. Now my last example, we still set it equal to 0. It factors as well, x minus 5, x minus 5. So we have the same 0 here, x equals 5. So we just treat it as 1, 0. But this is going to lead us into the next discussion of how do we create, whoops, not negative 5, positive 5, because x minus 5 equals 0. how do we create these going backwards? So if I give you the 0, we should be able to create these functions by going backwards. So when we have a 0 of a function, then we have if we put that value in, we're going to get 0. It's also called a root. R comma 0 is a point on the graph when R is a 0 of a function. And x minus r, which is what we're doing right here, so if 5 is our 0, then x minus 5 is a 0. If 0 is a function, then x minus 0 is a function. If negative 3, x minus negative 3 is a 0. Is a root factor. Sorry, it's a factor of the function. All right, so we're going to work our way backwards. So this is just working our way backwards from factoring. So our function is going to be, in this case, x minus 3 for this 0, x minus negative 1, and x minus 1 for those 3 zeros. So this one's going to be x minus 3, x plus 1, and x minus 1. So, and we could put a value of a in front of this, but it would still have the same zeros. So if we could put another number in front of this, there could be several functions that have these 3 zeros. So if we multiply this out, we're going to get x minus 3 times x squared minus 1. So our function is actually x cubed minus 3x squared minus x plus 3. So that's the function that have these 3 zeros in that function. We multiply this together using FOIL. All right, and the final thing here is if we have multiple roots, like we had up here in this problem right here, right here, then we have multiplicity, what we call multiplicity. This one was x minus 5 squared. So we're going to have what we call multiplicity on things that have multiple roots, like this one. This one has a root of 0, so x equals 0 is going to be my root here, but it has multiplicity 3 because of the power. So the power on the root is the multiplicity of that root. And in this case, x equals 3 is going to be a root for this one, and it's going to have multiplicity 2. And then we're going to have our final root of negative 1, and it's going to have multiplicity. It's not going to have a multiplicity, actually. It doesn't have, you could write it as multiplicity 1, but it doesn't really have multiplicity because there's no power up here. So only the ones that have powers greater than 1 do we state that they have multiplicity. Now on the graph, multiplicity is meaning, it's going to mean whether it crosses or if it just touches. So in this kind of function right here on a graph of this is a positive, so that means it's got a power of 3, 4, 5, 6, so it's an even one. So the graph is going to look like an even one, and it's going to cross through 0 on the graph. It's going to cross through 0 this way because it has multiplicity 3. So any odd multiplicity, it's going to cross through. But at 3 here, it's actually going to, I don't know if what it does here, but it's going to just bounce off of the intercept because it has multiplicity 2. And then it crosses again at negative 1. And I didn't have this one. Crossing at negative 1. So we have some things here that are going to look at this graph. We know what I'm trying to say here is that when we have a multiplicity of odd, then it's going to cross the axis. This one crosses the axis. The graph does. This one is just going to touch the x-axis because it's even multiplicity. This one's going to cross the x-axis. So you can tell by the multiplicity whether the graph's going to touch or cross the axis.